I hope and pray that you are well. We are quite close to the end of semester. I am on lecture 14. Well, this is a very important study material. Rather, it is the key of the topic which I was teaching, that was the inorganic electronic spectroscopy. Now we have come to the stage that we will be able to interpret the spectra of complexes. Well, this is just an example you can see in your notes. This is this complex, vanadium complex, chloro complex, and this is its spectra. I've taken it from the book. Well, what is this band and what is this band? Okay, this comes at higher frequency energy and this comes at lower. There are only two bands. Okay, will there be only two bands or three or four and something like this? And similarly, besides this thing, that is interpretation, what this band represent, which transition is responsible for giving this band or peak, which transition is responsible for giving this peak. So this is all explained with the help of Tanabe Sugano diagram. Well, I have given you full one lecture material on Tanabe Sugano diagram, lecture 13 I mean. Here is a Tanabe Sugano diagram for D2. One of my student, MPhil student, if you see the books, they are not like this. But one of my student, he has made this small deviant Tanabe Sugano diagram. Instead of just 0, 5, okay, we have divided it, okay, in 5 units and so on and so forth. So this diagram is only representing the triplet state, T2G triplet, T2G triplet coming from P here. I should have written here P, and similarly A to G triplet. This is the ground state, T1G triplet. So in Tanabe Sugano diagram, the main thing is energy over B, Raka parameter or interelectronic ripple. They are plotted against the ligand field parameter delta octahedral over B. So this was the thing which Tanabe and Sugano did. They involved interelectronic repulsion and also ligand field parameter. So the second important point which I described before is that the ground state is always taken as the x-axis. So all the transitions will go from here up, wherever they go. Now let's come to the material. Today I'm going to talk on use of these diagrams, which I have explained you once again. For what purpose? For interpretation of the UV visible spectra of transition metal complexes. Well, please note it. This is again a very important topic. This is going to help us assigning bands to transition. Okay, well, and then it is also going to help us determine what? Delta octet and DQ. From just spectra, we will be able to do this, determine this. Then Raka parameter, which we just heard of, we can find out the value of this inter-electronic repulsion parameter. We will be able to find, and then the bonds between metal and ligand, what percentage is the covalent character and what percentage is the ionic character. Okay. This we can find out. Here is the question I have framed, and I am going to solve this in very good details. Although it can be solved whatever time I've spent, even 1/4 of the time we can do it. Absorption spectrum of a vanadium complex I've given. Okay, in reciprocal centimeter is given below. Well, here is the reciprocal centimeter scale. This is energy scale. The nanometers are also given. If it is given in this scale and this is not given, then we have to convert it. Okay, so first of all, we try to see there are two bands, this one and this one. So we will just suppose that mu1 is the lower energy band and mu2 is relatively higher energy band. You can see that this is 15,000 something, and I have marked it. It's little above, so 16,400, and this is 26,200. I have just put a dotted line so that you can understand. The energy of mu this band is this. Energy of this band is this. So this is about it. Let's see. Step one, what we do? Well, simple. You have, this is the complex. Find out what is the oxidation state. It is this. And then what is the configuration? Well, you can write the configuration, you know it well. So D2 comes. So we will take D2 Tanabe Sugano diagram. Okay, we have Tanabe Sugano diagram for D3, D4, D5 and all that we have. So we will use this diagram, D2 diagram. Okay, and then I have written if the lambda max is given in nanometers, then we will convert it into the reciprocal centimeters. So that has also been done. Okay, so in this spectrum only two bands, mu1 and mu2 are visible, but mu3 is not visible. Let me go back to this one. mu1 and mu2, you can see that. Okay, now this is higher enough. The third band is coming right here. It goes from somewhere, it comes here as high energy band. So that is not visible here. Okay. So mu1 and mu2 are visible, whereas the third band is not visible. It comes at higher energy, beyond 35 reciprocal centimeters. So what we are doing is we suppose that this band, mu1, is because of this transition. Look at this, please. This is mu1. This is the first energy level from ground, T2GF. Okay, so from this to this, energy is less. If it is from here to here, then it is more energy, that is mu2. I have shown it here. So I think when you will read it, you will understand it. The peak mu2 at 2600 is due to transition, okay, T1G from here to T2GP. Here it is. T2GP is here. And it comes from P. Okay, P triplet P. This is F, please. Okay, So once we have supposed that this is this and this is high energy peak and that's the low energy, then the experimental energy ratio. Naturally, 2600 divided by this. This we get from spectrum. So experimental energy ratio, this divided by this is 1.59. Now, with the help of Tanabe Sugano diagram, whatever we do, we have to find out delta octahedral over B, this value, at which the energy ratio E2 over E comes equal to this. This we can do with the help of Tanabe Sugano diagram. That was experimental. This will give us theoretical value of all that. So the method which we use is called hit and trial. To understand this method, it is better you take a full page photograph, okay, photocopy of D2 small deviant Tanabe like this. I have already sent you this one, okay, and it is given on page, the next page it is given. Okay, and also see the table which is given on page 7. I will show you in a minute. So to begin with, let us determine E1 over B energy, E1 over B and energy E2 over B values for delta equal to 5, 10, 15, 20. See here in this diagram. Here is the energy delta octahedral 5, 10, 15, 20 and so. So what we do? If we want to find E1 over B at 5, go up, then make a left. You can see that this is how many divisions? 1, 2, 3 and 4. For delta octahedral over B equal to 5, this value is only 4 divisions. I have put it in a table. I will show you in a minute. But come to 10 now. This is the first T2G energy, that is mu1, E1 energy. So this is now at 10. 10, go from ground state to the first excited state. Okay, it touches this line here. Then make a left. The value which comes of E over B, in fact it is E1 over B, will be how much? 5 plus 6, 7, 8 and 9. Let me show you. And similarly at 15, go from here, you go up. Okay, from this level to this level. And then make a left and come here. This is 10, 11, 12, 13. Let me show you the table so that you understand what I am saying. Here it is. Table 1. Table 1. Diagram. Tanabe Sugano diagram. Okay. Okay. Here is 5. And we calculated that it is 4 divisions. E1 over B. Then 10. Delta octahedral 10. This is 10. Make a left, and this is, you can see, is 9. With 15, go up from ground state to this excited state. Make a left, and you can see it is 10, 11, 12, 13. Where it is? It is 13. Similarly, let us say go to 30. Okay, 30 is here. Go up there. You keep going, it touches here. And then you make a left. And you will hit across 40.8. Okay, so this is how you develop the table. Now, if you notice, there is another thing which we have to do. This is the first, okay, state, and this the second E2 over B. This was E1 we have found out. E2, where is E2? At 5, delta octet equal to 5, E2 over B. E2 should be this one, this line. When this goes up, okay, and it touches the second T1GP excited state line. So you can see the value which comes for that is E2 over B. Sorry, wait a minute. E2 for 5, E2. Okay, please, we are now going to find out the values for E2 over B. Okay, at 5, 10, 15, 20 like this, delta octet over B. What is the value of E2 over B? We do it the same way as we did it for this one. Let's see 5. 5 delta octet, it is 5 is here. And now let us see the transition. This second excited state is this one, please. Okay, see this comes here, okay, and your A, okay, you will lift it up like this. It touches it here, and you make a left, and you can see it comes here at 5. Lower red arrow, 18.4 I have marked it. Come to 10, 25.5. Let's verify it. 10. And where is this excited state? This one coming here, here. And this 10, okay, let's go up. And it touches it somewhere here. Then you make a left, and you will see it will be touching it okay, E2 25.5 at 15. It's going to be, okay, we go up, straight up like this. So it touches this line, the second one, okay, here, and then you make a left, okay, and then you get, so in the same way, you get all these values. Now, if you notice, the next step is dividing this with this. So you divide 18 by 4, you get 4.6. 25 by with this, you get this. So E2 over E1 value is gradually decreasing. You come to 1.56, which is the experimental. So what we see is it is better now that we further do the increment, small increments, and find out the exact value. So we take 15